right. So this is a final update on the work I've been doing to rejuvenate silicon probes for acute neurophysiology. Almost a year ago, I gave the first presentation, and it's nice to be wrapping up and have the preprint out. Oh, doesn't. Oh. Okay. So silicon probes have changed the way we do neuroscience. In our lab, we've adopted them from heptodes and tetrodes in order to get more cells per day, reduce our damage to the brain with these probes are more flexible. And as you can see, it gives us, in the cerebellum specifically, it gives us a picture of the cell that we wouldn't otherwise get, specifically in this case, Purkinje cells, which have a different spike shape depending on what part of the cell you're in, and you're able to tell the polarity of your cell, what layer of the cerebellum you're in, and which direction you're going in based on the waveforms that you see when recording on these multi-contact, sort of almost like a picture of your waveform shape. And so that guides us in our ability to identify our neurons. It guides us in our understanding of our modulations, what we're looking at, and how we can better record from the brain and the region that we're in. To give you an example here, we have our molecular layer up here. You have your Purkinje layer here and your granular layer here, and then another Purkinje layer and molecular layer. This is the pretty typical structure of the cerebellar cortex. And by having this layer structure, when these neurons are unlabeled, we're able to go in, look at which way our Purkinje cell is facing based on the simple spike or mostly the complex spike shape. So it's a inverted, negative waveform in the dendritic tree, and then it becomes this more varied waveform shape, positive waveform shape in the soma. And this allows us to more thoroughly label the cells that we see, and it gives us a better idea of where we're recording from and what we expect in our modulations. Given that, the probes that we use are silicon probes with conductive polymer coating. These probes we use Cambridge Neurotech probes, but overall, these probes tend to have a couple of different configurations. One of them is with a smaller footprint of recording where the contacts are closer together and they're more spaced out in a both X and Y direction. So you get more of a spatial picture of your neuron. There's also, if you want to record more depth, if you want a better idea of your structure going into the brain, you can record with just a linear probe, and these have one strand of contacts down a larger span. Now, the probes that we use, they have 64 contacts. You can buy probes with more, but it's kind of bottlenecked because they're passive probes. It's kind of bottlenecked by the size of your connector and how many wires you can fit on the probe at a time. These probes have a 12 micron by 12 micron contact size. So this right here for both probes. And we're able to record from most of the neurons that we would like to. So we use these silicon probes to record acutely from the cerebellum of the common marmoset monkey. So this is a picture of generally where we're recording from. We go to cerebellar cortex and nucleus. We record from lobules 6 and 7 of the cortex for tongue and eye modulations, and then we also do the same in the physical nucleus. We basically target by way of CT and MRI, and we're able to, with these probes, that are around 10 millimeters long. We're able to go depths of, they're 15 millimeters long. We're able to go to depths of 9 millimeters to find the structures that we're looking for, which is really good given that in primates, it's pretty hard to reach the cerebellum because most primates are much larger. Our marmosets are smaller, and so we use tools that are mostly designed for mice and rats in a primate species to hopefully be able to conclude things about primates in general and the circuits that are they're in. This I'll show you is a I would say a pretty typical day of recording with these probes. As you can see before I run the video, this is a view of the different channels that we have on our probe, and this is probably 15 or 20 channels. And you can see that there are spikes on most of them. We get a pretty good density of cells in our recordings, and on a good recording day, we'll get somewhere between 50 and 100 neurons with our 64 channel silicon probes. But here's a video of a Purkinje cell that we have on the channel that we're seeing here. This is the PCA representation of the spikes at the threshold, and you'll see that the yellow is the simple spike of the Purkinje cell, and then the green you'll see kind of sparsely pop up and with a lower kind of bassier, lower frequency noise. Those are the complex spikes. So. But you can see that spike that was popping up here, that was our complex spike. What we believe to be a learning signal in the cerebellar cortex. All right. So the conductive polymer coating on these probes is an improved. So when you minimize the contact size on probes, your impedance increases. It reduces your ability to pick up the electrical signal from these small cells. And so in order to deal with this problem, what a lot of companies do is they'll coat the contact, these very small contacts, with a conductive polymer. And the way that they do that is, or the mechanism behind this is increasing the surface area by almost putting like a fuzzy structure on the contact. And so you'll see that so this is a picture of one of our probes, brand new out of the box. And you can see that here the lines, they're gold. So the contacts as well are natively gold. And then you coat them with this conductive polymer, and the conductive polymer actually makes them darker. It creates this green, blue, sometimes black, depending on the thickness of the coating, on the contact. And you can see here as well, these are bare contacts on a laminar probe, and the coated contacts are darker. And essentially what that does is it increases the charge carrying capacity for the contact. And this is another paper where they tested the thickness of, or they essentially, during the electroplating process, they varied the current to electroplate. And so you get different amounts of conductive polymer coated on the surface. And so this is less, this is a little bit more, this is a little bit more, and you can see that the surface gets this fuzzy sort of bushy coating on it, and that is what allows more charge to be carried to the probe and in turn read by your amplifier. This process is done through electrodeposition. Basically, you create a current bias through an electrolyte across a reference electrode and your own electrode contact. And so we do this with these probes come coated out of the factory in this way. And I'll be presenting a way to do this in your own lab in order to rejuvenate these probes later in the talk. But it creates this charge density difference, and the polymer, which is doped with they use a dopant to essentially break up the polymer. Otherwise, the polymer would be very tight to each other. So they use something to kind of spread out the polymer molecules in order to create that fuzzy surface. And that allows, it gives you the properties of the polymer, conductive polymer, while also creating a surface that is conducive to carrying more charge. And so this process is a pretty well-documented process with many different types of conductive polymers. But in this case, we use a gold substrate with PEDOT PSS as the conductive polymer and dopant. So PEDOT PSS is a popular coating for acute probes. It's biologically inert. It allows it works really well on small electrode surfaces, and it lowers the impedance at biologically relevant frequencies. So we look for our in our recordings, we tend to look at signals in the action potential band between 300 hertz and about 6,000 hertz. In order to better get these signals, we would have to find a conductive polymer, or there is a conductive polymer, PEDOT PSS, that lowers impedance at those particular frequencies, which leads people to believe that this is an improvement, which it is. You can coat these electrodes. So this is a paper that tested frequency or magnitude and phase of impedance for different size electrodes at different frequencies of impedance or impedance measurement. And so essentially to orient you guys as to what an impedance measurement means, how we take that impedance measurement and how we display it, I'll direct you to these. So this is just a plain gold contact, the measurement of a plain gold contact at different sizes. So they pattern different size gold contacts onto a circuit board, and they ran, they did a standard electronic impedance spectroscopy measurement, which is basically you're stimulating the contact of the electrode with a sine wave, and this sine wave has a frequency here of the sine wave varies in frequency, and you take this measurement at varying frequencies, which tells you what the characteristic is of that electrode at the frequency that you're measuring. And so if we were to get a neuron with a frequency signal component of around 100 or 1,000 hertz, you're going to look at this frequency band here as what the characterization, how that will affect how you pick up the signal. And so the impedance magnitude is just a measurement of the magnitude of the wave that comes out that we're measuring through the channel or through the electrode. And then the phase is how much phase has been shifted in that original signal. So in this case, you can see that the bare gold contact for, let's say, so our electrodes have about a 12 by 12 micron footprint. And so that would be kind of akin to this 15 micron diameter electrode here. And so if we're looking here, you have your 15 micron electrode contact at about 10 to the 9th impedance magnitude, whereas when you coat it with PEDOT, your impedance lowers to about somewhere between 10 to the 7th and 10 to the 8th ohms. And then in this case, when you're looking at the phase as well, you're going to get so you have a lower phase here, and then you're essentially it doesn't impact the phase that much, but it does much more at with smaller smaller electrodes. So to give you guys kind of an idea of what these mean, this characterizes two distinct properties about the electrode. So the impedance magnitude, we kind of relate it to the resistance of the contact. And you can say, okay, you want more charge to pass through your electrode, so you want your impedance to be lower. You want essentially what a lower resistance. And then with phase, so a perfect capacitor has a negative 90 degrees phase. And so we want to carry a lot of charge. We want our electrodes to have high capacitance. And so you basically, the more negative your phase is, the better your electrode is as well. So in both instances, we're looking for a lower impedance magnitude and phase to characterize a better electrode. And so as the electrodes get worse and worse, you'll see the impedance go up. In addition to that, so these are studies on how the thickness of the coating kind of affects the characterization of the electrode. In this case, they varied the thickness of the PDOT coating, and it plateaus at a certain point. And so there really is a sweet spot where you want to apply this coating, but there isn't much of a point of applying too much more than that. And so keeping that in mind, we look at our own electrodes and we see this effect of the coating degrading over our recordings, leading to increased impedance. So a common thing for labs to do during their recording sessions or before the recording sessions is to record the impedance of the electrode. And that gives us a relative measurement of how good your electrode is. How well are you going to be able to pick up signals in the brain today? And so throughout all of the time that we've been using electrodes, we've been taking a pre-recording impedance measurement. And so something that even before I got into this lab that was noticed was that over time, the impedance of these polymer coated silicon probes increases. And it gets to the point where you're, a couple order of magnitudes almost increase from your base impedance in the magnitude spectrum. Well, I guess one more order of magnitude approximately. But in addition to that, you're also losing your capacitive properties as your phase increases. We kind of quantified that in terms of the idea of bad contact. So at a certain point, we noticed that after your average impedance of the probe goes above 150 kiloohms, you're going to have a reduced ability to isolate good neurons. And so we've called on those particular contacts. And so we've called those bad contacts. And so it's a little bit ununiform due to the lack of standardization of cleaning protocol, handling protocols in the earlier days before we were trying to quantify this. But generally, you have an increase in bad contacts every day that you record. And so just to kind of give you guys an idea, well, first of all, just a note, impedance magnitude plots, they almost always are going to have a log scale. So keep an eye on that. And then impedance phase is usually a linear scale. You see the effect is more clear in that. And it's also, impedance tends to change on order of magnitudes rather than, rather than increasing by a certain amount. You're usually getting a percentage increase every day. And so what over 12 probes or I guess in this case, this is 7 probes that we had a significant number of pre-recording measurements for. We calculated average of 22% increase in impedance magnitude per day. And this is just to orient you guys to these plots that you'll be seeing throughout the presentation. Each one of these box plots represents one probe, and that is 64 contacts. So the spread of the box plot is one measurement for each of the 64 contacts. And as you can see as well, these probes on day one were brand new, and they have about an average impedance of 50 kiloohms. Most of these probes come with an average impedance of 50 kiloohms, and that's what we sort of set as our expected new probe impedance, but also what we would hope to get back to if we're able to rejuvenate these probes. And I'll show you guys how that happens. In addition to that, our impedance phase tends to be around -60, -50 when the probe comes to us brand new. In addition to that, we wanted to kind of see if we could physically see a change in these electrodes, and we were, and so we got a microscope and we were like, okay, what does it look like? What do these contacts look like? What is this coating? Does this coating look like something? Can we quantify, or can we see it and be able to tell if an electrode is bad with just a microscope? And in this case, yeah, it was pretty obvious. So this probe here is a brand new Cambridge checkerboard probe. You can see the contacts are like a darker green, almost blue color, and that generally means that the coating on them is pretty good. The PEDOT coating is brand new. You're going to have an average. So in this case, the probe was really good. You had an average of about 40 kiloohms impedance. But then you look at this used probe, and just to note, the coating does not necessarily wear evenly, depending on where you're recording from, how hard it is to get past the dura, and just general effects of the ePhys recording process. You can have different contacts wear differently. And in this case, you can see that the lighter contacts, they're like a gold color, which the contacts themselves before coating are gold. And so you're basically seeing the bare contact here. And when you measure the impedance on it, you get a mega ohm of impedance, which is way too high to really record anything on it from our experience. And then in addition to that, you can have some darker ones. So you can see here that these darker contacts are 37 kiloohms. You have this like medium light one over here that's 164 kiloohms. And so it seems to us that the fidelity of the coding is directly related to its impedance measurement. Now, another thing that we noticed is anecdotally, or non-quantifiable, we did not quantify it, but over time, we would see that the size of the units that we could record and the number of units that we could record was greatly reduced. And so you can see here, we would get some really nice units. This unit is almost, 1,500 microvolts. That's a big cell. And this is on day 2 of using the probe. And then you use it and you use it and you use it again. And this is the best unit from the 7th day of recording. And as you can see, if you're only getting units that are this much higher than the noise threshold, imagine all of the other units or the lack of units that you're able to record because of this change. And we were noticing over time that our number of units would reduce. And so this is something that we saw in our probes, but we were curious, do other people see this? Is this something that we're able to see on a larger scale? And we asked other labs, and it's pretty well understood from other labs that probes like these do degrade over time, or that you have to buy new probes over time. But looking at the literature, it wasn't terribly obvious if impedance directly affects signal quality. And so there have been quite a few studies. These are just 4 of them, but I want to say I found like 10 or so that try to, in a sense, quantify the impact or the correlation between impedance and signal quality that you get during a recording. And the answer is sort of. Some people did find it, some people didn't find it. And in some cases, they may have seen it a little bit, but it wasn't significant, or they just flat out didn't see a correlation. So with this study, they patterned different this is a pristine iridium contact, and then they patterned either PEDOT PSS or like a fuzzy gold coating on different electrodes. The PEDOT PSS coating, they did find a difference in impedance measurement between a non-coated and a coated electrode, but there was no difference in the recording signal sizes. So here, no difference in peak-to-peak amplitude, but there was difference in uncoated versus coated when measuring impedance in saline or in the brain. And so this one says kind of not really. This one over here, so just to as a note, these two studies use in vivo recordings in anesthetized mice. And so obviously our recordings are in awake behaving marmosets. Maybe the results do not translate over. But in this case, this is bare gold versus PEDOT, and they said that they did find a significant difference in the spike size on a contact, but there wasn't a lot of quantification of that effect. And then in this one, there was no difference in signal quality for gold-coated iridium probes, so not necessarily PEDOT PSS, but a different type of impedance, high impedance versus low impedance situation. And then in this one, they actually, I found a lot of studies where they take the impedance measurement in the brain as a way of quantifying a chronically implanted electrode. And that, even though they had a greater number of well-isolated units versus an uncoated probe, their ability to quantify how impedance was a factor in that was relatively low because they're always taking impedance measurements in the brain, which is more of a function of how much glial encapsulation your probe has at the time. And so there really aren't any studies out there that try to directly quantify how impedance has an effect on signal quality of a recording. So we did that. We have 61 days of recording where we have both a pre-recording impedance measurement in saline and a count of the number of units and the magnitude of the units on each contact. We took these 61 recordings and we basically said, okay, we're not going to treat them as a single probe. We're going to treat each contact individually, and we're going to organize them into 4 groups by the magnitude of contact impedance. And so you have your 4 groups here, and you can see that this is the distribution of spike magnitude on each contact and median spike magnitude on each contact. In this case, you can see that the median of each group goes lower and lower and lower as your contact impedance goes up. We find that, we really stop isolating good units around the 150 kiloohm mark, which you can see here. You can still get some, but generally a lot of yours are just zero, like you just have no spikes on a channel. And so that's why this is so low, is a majority of your contacts have no isolated units on them, which is expected when your impedance is 800 kiloohms. In addition to that, we quantified the number of contacts with no units, and this, as you can see, went up significantly. And this is a significant slope as related to if you were to shuffle all of these and regardless of contact impedance and plot that, you have a significant difference. And then in addition to this, this is the median contact impedance for each of these groups, and this is also significant. So we found a pretty convincing argument for the fact that there is a direct relationship between impedance and reducive capacity to isolate good units, which is nice because it was exactly what we were seeing in our recordings. You'd record for a few days, you get less and less and less and less. So in addition to that, we wanted to tackle another problem, which is that we would pull the probe out of the brain and you would see tissue deposit on the probe. And, you know, you talk to any lab and everyone has a different way of cleaning their probes. There's a few different kind of accepted methods, but we actually had a way of doing this that originated before I got into this lab as a way to remove fibers from a curtain that was adjacent to our recording chamber. And basically what was suggested to us and what we figured out worked was to penetrate the probe into a hard-boiled egg, and that would remove the physical gunk from the probe, and then it would be clean. And there was no other way to do this because these probes are so fragile that if you try to use tweezers or you try to do it in any other way, that you're probably just going to break the probe. And, you know, we needed to do this because not only was the probe, you know, you just saw physical debris on it and you don't want to put that back into the brain, but the debris blocks signal from getting to the contacts. So your signals would be worse if your contacts were covered in this debris. And in addition to that, we always penetrate here. I'll go back to this picture. So this here is a layer of Duragel. It's like a silicon, a two-part silicon substrate. We use this almost as a support when we're trying to penetrate into the dura because we don't do a durotomy. And so this flimsy probe has to penetrate into the dura, and this Duragel gives it a nice support to do that. But your trajectory through the Duragel, which is important for targeting the right structure, can be affected by any of this debris or fibers on the probe. And so when your probe looks like this little gunk here might get stuck on the Duragel and divert your probe left or right, depending on which direction you're pushing it. And so this debris becomes a big problem for us. And there's a lot of debate about how to clean it. Previously, when we were using heptodes and tetrodes, we'd use Tergazyme, which is an enzyme cleaner from Alkanox. But in this case, I'll explain why we ended up stopping that use. But we found that our best way to do this would be to do an egg cleaning, which I'll show you here, and then after that, soak it in trypsin overnight. Trypsin is a cell dissociation media, and it sort of does a chemical clean of the probe without harming it. So this is actually, I took a video of our egg cleaning process because I get questions on it all the time. What are you actually doing? Are you actually sticking a probe into a hard-boiled egg? And the answer is yes, and this is how we do it. So we're using a micromanipulator attached to the probe, and the egg is sitting on a flat surface. And so essentially what you're doing is you're just allowing the micromanipulator to push it into the egg, and that physical physical pushing, the egg closes around the probe, as you'll see here, and it almost pushes the debris off of the probe. So you see there, it pushes that gunk away without damaging the probe. And yeah, so that's how we get a clean probe, and we spray some alcohol on it in between, and then we do it again. And what you can do is if you do it a couple of times, you can move it over into a new hole in the egg, and then you redo it, and over you basically iterate this process until you get a clean probe, which looks like this. And you can see here that the contacts don't have any gunk on them, and it looks quite a bit like this. And that process has proven to be work quite well for us without damaging the probe, and also, you know, restoring the functionality of the probe to an extent. Now, keep in mind the previous plots I showed you. These plots are with cleaning, and so despite cleaning the probe every single day, we still had an increase in impedance. However, cleaning the probe itself worked pretty well with this hard-boiled egg then trypsin process. So basically it reduced the number of bad contacts. And so what we were observing was that when you would get this tissue debris on the probe, your impedance would go up a lot on a few channels. And you could literally see on the channels that you had the debris, when you would measure the impedance, only those channels were super, super high, if the probe was relatively good otherwise. And here, so let me give you some numbers. There was an 88% reduction in impedance magnitude, and there was an 8.2 degree reduction in impedance phase, and there was a 33 contact reduction in bad contacts with this process particularly. We also tested if the egg cleaning was safe for the probe. Here you can see these are brand new probes, so they're at about 50 kiloohms, and then we did an egg cleaning test. And so this is with 5 simulated egg cleanings. So essentially what we would do for 5 days cleaning it with an egg. And there was a median increase of 5 kiloohms and a standard deviation of 3 kiloohms. So 5 kiloohms when your probe is increasing by 22% a day. So in that case, you would expect your impedance to double just from degradation of the PDOT coating. 5 kiloohms is not that much. And in addition to that, this was without the trypsin. This was just testing the egg. And we believe that the trypsin actually, that sometimes what can happen is that the egg can get a little bit of egg particles on the probe from the cleaning process. And those are easy to remove with alcohol or trypsin. And in this case, that's why we use the second step of trypsin to alleviate that problem. And so the egg cleaning is safe and it works. The egg then trypsin cleaning is safe and it works. Yeah, and so that's what we use as our standardized procedure now to clean the probes every single day in between recordings. In addition to that, we thought, we had been using Tergazyme to clean the teptodes and tetrodes, and then when we used it on the silicon probes, we realized that it's not really doing what it's supposed to do. It was kind of messing the probes up, and so we decided to quantify this process. And so we saw that the the Tergazyme was actually stripping the PDOT coating off of the probes, and you can see here that so these are just the impedances of a kind of dirty probe right after coming out of the brain. They're about 200 megaohms, 150, 200 megaohms, or kiloohms. And then when you put them in Tergazyme, and the Tergazyme strips off all the PDOT, and all of these probes become very, very high impedance, which is like a uncoated new probe. And so you can see here, all of the contacts are gold, and these gold contacts don't have any PDOT on them, and therefore their impedance is very high. This process obviously is not good for cleaning the probe in between recordings. It kind of ruins the PDOT coating. And so we were like, okay, we don't think we can use this to clean the probes. But it ended up being super helpful when we decided, okay, due to that gradual increase of the PDOT coating degrading over time, over recordings, even when we do clean the probes, we want to recoat the probes. We want to try to renew this PDOT coating. How do we do this? Well, first we tried just cleaning the probe with our egg and trypsin protocol and then recoating it, and it didn't work. Even though the probe was clean, the PDOT would not recoat onto existing PDOT coating, or a degraded existing PDOT coating. And so we're like, okay, what happens if we use the Tergazyme to completely remove the PDOT coating and then recoat the PDOT through electrodeposition? And that actually worked very well. And you can see here, this is actually the same data as the previous slide. So you saw after recording, the probes were at about 150, 200 kiloohms. And you can also see when you have a dirty probe, or you have a probe that has been put in enzyme cleaner, the spread of impedance is very high. You have very high variance in your impedance. Essentially your PDOT coating is unevenly worn. And so, and I would say in general, the Tergazyme stripping process is fairly even. It brings most of your impedances up, but at the same time, I think it's something about treating the PDOT coating with the tergazyme, removing most of it, that allows PDOT to be replated. And so this process, this tergazyme stripping here, allows us to recoat our electrodes and bring them back to, here you can see 50 kiloohms, a little bit less than 50 kiloohms. These probes are essentially as good as brand new. And which was fantastic because we were basically spending a bunch of money. We would throw the probe out as soon as it was bad. And now we're able to take these probes that we would otherwise have thrown out and we recoat them and they're almost brand new. And the restoration was in the phase as well. We were able to get them back to what we would see pre use in new probes. All right. And so, the golden question is, if you're recoating these probes, does it make your signal quality better? And I would say the answer is yes. So this is from a probe that we used for 9 consecutive days of recording. You can see that the magnitudes are pretty abysmal. You're not that much higher than your signal to noise ratio. And this is the best unit of the day. And then we recoated the probe and we immediately got a fantastic recording with this almost twice as large neuron. And to be fair, it is your best unit and the number of units that you get are going to be somewhat dependent on where you are in the brain. And so you can't just rely on one day of recording to tell you, or one day of before and after to tell you, are you getting a good effect? You definitely have to quantify it over more. And so we did this for 4 probes and we got a 57.4 microvolt increase in average spike magnitude. So on all 64 channels, your average spike magnitude went up. And in addition to that, we got a 27% decrease in the number of contacts with no units. And so we were able to just generally isolate more units on the probe. And yeah, so this is essentially shows that the recoating process works. We have good impedances, but we also have good spike amplitudes and we're able to isolate a lot of good units. And so the process works the way it's supposed to. Yeah, and I just want to thank everybody who helped me on this project. I mean, Natasha ran a ton of my experiments. I mean, and all you guys have reported impedance data, and I mean helped with the initial testing of all of this, starting the recoating process and figuring out how to take pictures of the electrodes. And then, Paul Simon took a ton of data from before I came into the lab. I wouldn't have been able to have as many probes, as many days of impedance measurement without you guys. So yeah, thanks all. And of course, Reza for thank you. All right. Yeah. And most of all, our adorable little subjects, Mirza, Ramon, and Charlie. Thank you for your data. Yeah. Any questions?
What's the idea to use it? Or your idea?
No, hold on.